All right, let's go on. We're going to find dy. Notice how it doesn't say dy dx, but just says find dy for y equals 2 squares of x over 3 times 1 plus the square root of x. Well, that's what I'm coming over here to do. You know, you're basically finding your derivative. It's just that you're solving your derivative dy dx just for dy, so multiply the dx over. But start out the same process. So y prime or dy dx for this function, because it's in the fraction, we're going to use our quotient rule. So the bottom times the derivative of the top, and that will be 2 times, I guess if you want to write that as 2x to the 1/2, that's what that top is right there. So if I drop down the 1/2, x to the negative 1/2. Okay, so let's double check, make sure we got this right. So bottom times the derivative of the top, just pull the 2 off and just focus on the derivative of x. So pulling down the 1/2 x to the negative 1/2, okay, minus the top times the derivative of the bottom. Okay. Well, if we kind of want to look at the bottom, maybe if we want to distribute that 3, we can write it as 3 plus 3x to the 1/2 power. So when I multiply by that times the derivative of that, obviously the derivative of 3 is 0, and then we'll get 3 times 1/2 x to the negative 1/2. Okay, all of that over our bottom squared. So I'm going to leave the bottom, though, this time as being like this. Maybe it'll be easier to clean up. We'll see. Okay, so dy dx is going to equal 3 times 1 plus the square root of x. Obviously 2 times the half is going to cancel, and you'll get x to the negative 1/2. And let's see, that 1/2 is going to cancel with that 2 there. So we will get a minus 3 x to the 1/2, x to the negative 1/2. So obviously these two x's are going to cancel each other out, which is kind of nice, but we need to see that first of all. And if I square this process, I can maybe write it as 9 and 1 plus the square root of x squared. Okay, let's just keep on cleaning this up. So dy dx, let me distribute, basically here, let's try to distribute the 3 and the x to the negative 1/2 together into this fraction, or into this first parenthesis. So 3x to the negative 1/2, and then be plus 3x to the negative 1/2 times x to the positive 1/2 minus 3. So again, paring's going to go away. All over 9 times 1 plus the square root of x squared. Okay, so dy dx is equal to, it looks like 3x to the negative 1/2. A positive 3 and a negative 3 go away. All over 9 times 1 plus the square root of x, all of that squared. 3 reduces into 9. And if we want to write this without negative exponents, then it's going to be 1 over x to the 1/2 and 1 plus the square root of x squared. And again, the problem just wants this for dy, so all we have to do is multiply the dx over. So dy is going to equal to dx over, and I guess if I want to write x to the negative, or x to the 1/2 and square root, I could if I wanted to, but square root of x, 1 plus the square root of x squared. And that's the equation for dy. Alright, so moving on, let's go to example number 5. With this one right here, we again want to just practice finding dy. So, and it looks like since I have powers of y, I'm going to involve some implicit differentiation here. Okay, so x times y squared, we've got a product there. So it's going to be first times the derivative of the second, which will be 2y dy dx, plus the second times the derivative of the first, which is 1. Okay, minus 4, and then the derivative of x to the 3/2 will be 3/2 x to the 1/2. And then the derivative of y, of negative y, would be like a negative 1, but then dy dx equals 0. Okay, so let's work some more on this just a little bit. We have 2xy dy dx plus y squared minus, looks like 6x to the 1/2 minus dy dx equals 0. And then since we have dy dx into two terms, let's bring those terms together specifically and kind of factor out the dy dx. So we'll get 2xy minus 1 dy dx. And then if I want to go ahead and I guess move those other two terms over, because I know I'm going to eventually want to solve, just get the dy by itself, there'll be a positive 6x to the 1/2 and a negative y squared. Okay, so dy dx, dividing off that coefficient over there, will be 6x to the 1/2 minus y squared over 2xy minus 1. And then to finish this up, just to get dx by itself, we can write 6x to the 1/2 minus y squared. If you choose to put that in parentheses with dx up there, that's fine. Or we can put all of this in parentheses and then just put dx over there. And that'll be the exact same thing. Going to example 6. We're going to find the same thing for cosine x squared. So dy dx is going to be, let's take the derivative of cosine x squared. Well, the derivative of cosine is negative sine x squared times the derivative of our angle, which is 2x. So dy dx is equal to negative 2x sine of x squared. And then just to get dy by itself, that'll be negative 2x sine of x squared dx. So not too hard of one. It's a good one to kind of wrap that little group up with. Right. So example number 7. We're going to do something a little different here now. With example 7, the whole goal here is really to kind of see the whole, are we getting much of an error if we use that linearization function that we've been practicing finding? If we use that, are we getting much of an error? And that's what this whole example 7 is all about. Okay, so for the following functions, they're asking us to do several things. First of all, we want to look at the change delta f in the function, and then we're going to look at the value of the estimate d of f, and then this last part is really going to see what kind of error we're getting when we're comparing the two. Okay, so what this top one represents the actual change, what's really happening. This is representing the estimate that we're trying to get using the derivative, almost like the linearization process. And then this third part is then telling us what kind of error we're getting. Okay, so for the first part, all they want us to do is just basically plug it in. So we want to find, for this function, x cubed minus x, we want to find f of, let's see, x naught, which is 1, plus the delta, or the derivative of x, or the dx part, the change in x, which is 0.01. So if I take the x value of 1 and I just change it ever so slightly, just by 1/10, okay? So in other words, we're finding f of 1.01, and then we want to subtract f of x naught, which is 1. Okay, so going into this function, then it's going to be f of 1.01, it's 1.01 cubed minus 1.01, and then minus the function evaluated at 1, which is 1 cubed minus 1. Okay, so if we do all that, what we're going to get is, looks like a function value of 0.02. Okay, so now let's go to, this is what's really happening to the graph whenever I change it ever so slightly. Okay, and let's look at number 2 then, the estimate of it. So d of f is going to equal to the derivative evaluated at 1 times the dx, and the dx is what's the change in x. We're changing it by just ever so slightly, which is 0.1. Okay, and you know, I just realized I was writing that as up above as 0.01 and not 0.1. Hey, but so we don't get a big difference here. Let's go back and change that just for a second, if y'all don't mind. Let's write that as 0.1, and then we need to change in there. All right, so give me 2 seconds to fix it. I'm going to put this on pause, I'll fix it, and then I'll get you a new answer. Just 1 second. Okay, so when I actually use the correct values, it's going to be 0.231. I'm glad I caught that. Okay, so now let's go back up into here. So we want to evaluate the derivative at our x naught, which is just 1, and then multiply it by the change in x, which is going to be 0.1. I want to say 0.01, but it's, yeah, 0.1. Okay, we need to take the derivative. So the derivative of our function, f prime of x, is going to be 3x squared minus 1. Okay, So let's look at this. The derivative then evaluated at 1. So f prime of 1 is going to be 3 times 1 squared minus 1, which is 2. And then we're going to multiply that times 0.1 to get an answer there of, obviously, 0.2. Okay, so then this is what's bringing on the third point, is that when we actually use the real function itself, we get a value of 0.231. When we use the derivative, this estimate, then we're going to get 0.2. And so with the approximation error, we're seeing what's the difference here? It's the difference in basically what we get from part 1, which is 0.231 minus 0.2. So together, when we look at this, then our error is going to be just simply 0.031. So very, very, very small error. So if nothing else, what this is showing you is that linearization process is really doing a good job of estimating what's occurring with the change in the graph at those exact points. Okay, for in this example, exactly at x equals 1. Okay, so let's do the exact same thing for part B. Okay, so part B, we're going to do the same process again. Let's do part 1. So part 1 is basically saying we want to find just the change in the function, which is going to be f, the function evaluated at x naught, so 2 plus the changes, make sure I write it as 0.1 this time, and then minus the function evaluated at our x value at 2. Okay, so it's going to be f of 2.1 minus f of 2. And that's going to give us, let's see, 2.1 cubed minus 2 times 2.1 plus 3, and then minus f of 2, so 2 cubed minus 4 plus 3. Okay, so when we look at this all together, what we're going to get for value for the change in f will be, looks like 1.061. Okay, so number 2, what we have to do now is use our derivative. Okay, so df, it's like the derivative of the function with respect to x. It's going to be the function evaluated at our x naught, which is a function evaluated at 2, the derivative, and then times dx. Okay, so df is going to be f prime of 2 times dx, which is 0.1. So let's come up here, and our function, the derivative of it would be 3x squared minus 2. Okay, so finding this out, then we will get 3 times 2 squared minus 2, all of that times 0.1. Okay, so when we evaluate that, then our derivative will be, let's see, 3 times 4 is 12. 12 minus 2 is 10, and 10 times 1/10 is 1. So it's just going to be a 1. Okay, so we look at the error then. The error is going to be really small because it's just going to be the absolute value or the difference, the magnitude between the two. And so it's just going to be a 0.061. Very, very, very small amount of error.